everybody. We have now a plenary talk by Professor Lina J. Karam from Arizona State University. The title of the talk will be Generative Sensing, Transforming Unreliable Sensor Data for Reliable Recognition. The abstract of the talk is as follows. The talk introduces a deep learning-enabled generative sensing framework which integrates low-end sensors with computational intelligence to attain a high recognition accuracy on par with that attained with high-end sensors. The proposed generative sensing framework aims at transforming low-end, low-quality sensor data into higher quality sensor data in terms of achieved classification accuracy. The low-end data can be transformed into higher quality data of the same modality or into data of another modality. Different from existing methods for image generation, the proposed framework is based on discriminative models and targets to maximize the recognition accuracy rather than a similarity measure. This is achieved through the introduction of selective feature generation in a deep neural network, also known as DNN. So, few words about our illustrious speaker here. Dr. Lina Karam received the BE degree in Computer and Communications Engineering from the American University of Beirut in Lebanon in 1989, and the MS and PhD degrees in Electrical Engineering from the Georgia Institute of Technology, Atlanta in 1992 and 1995 respectively. She is currently a full professor in the School of Electrical, Computer and Energy Engineering, Computer Engineering Director and the Director of the R&D Image, Video and Usability Lab at Arizona State University. She is also the president of Picaris LLC, a consulting company on media processing, compression, understanding, and analytics. Dr. Karam is an IEEE fellow, the highest grade level in IEEE, which is conferred each year to no more than 1/10 of 1% of all IEEE voting members for her contributions in the image and video processing, visual media compression and transmission, and digital filtering areas. Dr. Karam is a recipient of the National Science Foundation Career Award, NASA Technical Innovation Award, and Intel Outstanding Researcher Award, and IEEE Signal Processing Society's Best Journal Paper Award, and the IEEE Phoenix Section Outstanding Faculty Award. Her industrial experience includes image and video processing and compression development at AT&T Bell Labs, multidimensional data processing and visualization at Schlumberger, and collaborations on computer vision, machine learning, image video processing, compression and transmission projects with various industries, including Intel, Qualcomm, Google, NTT, Motorola, Freescale, General Dynamics, and NASA. He has over 200 technical publications, and he is an inventor on several issued patents. Dr. Karam has served on several journal editorial boards, several conference organization committees, and several IEEE technical committees. She served as the lead guest editor of the Proceedings of the IEEE special issue on perceptual-based media processing. She served as the general chair of the 2016 IEEE International Conference on Image Processing, technical program chair of the 2009 IEEE International Conference on Image Processing, general chair of the 2011 IEEE International DSP-SP workshops, and as the lead guest editor of the IEEE Journal on selected topics in signal processing. Special issue on visual quality assessment. She has co-founded international technical workshops and conferences VPQM at QMEX. She is she is currently serving on the IEEE Signal Processing Society's Board of Governors and the IEEE Publications Board as the IEEE Women in Engineering Liaison. She is a member of the Foundation and trains in Signal Processing Journal Editorial Board and of the IEEE Signal Processing Magazine Senior Editorial Board. She is also a member of the IEEE Signal Processing Society's Image, Video and Multi-Dimensional Signal Processing Technical Committee and the IEEE Circuits and Systems Society's DSP Technical Committee. She is a member of the Signal Processing, Circuits and Systems and Communication Societies of the IEEE. Let us listen to her wonderful talk.
It's working. Thank you very much. I'm very happy to be here at IIT-Hyderabad, and I wanted to let you know this is my first time I come to India. So that's my first trip to India, so I'm very happy to be here. But also this is the first time I realized I had to have a 27-hour flight to get here. So you have to bear with me. So I haven't slept except 4 hours during the last few days, but I'm really happy to be here and I feel energized. And thank you for the nice introduction. I would like to thank also our previous keynote speaker, because if you were here, he made my job easier. He talked about the explosion of data and the need for faster processing. So indeed, we're surrounded by data everywhere and sensors everywhere. And I would like to ask, who has a camera on their phone? Okay, so almost everywhere. See. So we kind of camera, so I use my camera on my phone, I don't use regular cameras anymore. In addition, they're introducing now IR sensors on the phone for face identification and others. And you'll see next, I'm not sure if you heard about the Google Soli, Google ATAP Soli. Anybody heard about Soli? This is an embedded millimeter wave radar that you could integrate in your phone. We happen to have one in our lab. It's very scarce, but we're working on some fun projects with that with Google that I can talk about. But what I'm going to do is show you a video. You don't need to hear the sound here, to show you how this enables interaction. It's like magic, no? So maybe in the past it would be magic. So that's how it is. This is a millimeter wave radar that can be integrated wearable mobile devices in your phone. Imagine what we could do. We're developing some natural interactions and interfaces with it, even authentication, heart monitoring or medical monitoring with that device currently in our lab. So more and more sensors are getting embedded everywhere around us and collecting all this data that we need to analyze. In addition, because we have a lot of data, we need help now. So we had machine learning come to the rescue for data mining and data analytics. And however, also advances in machine learning is driving more data sensing, because you have this network that needs to be trained. So both like machine learning driving the data explosion driving machine learning. And if you go to the Phoenix area in particular, in Arizona, you see these cars driving around trying to map the area, and you have all these sensors, radar, LiDAR, ultrasound, everything on the car to map the area. And now Waymo, it's an Alphabet Google company, Waymo Alphabet company, is offering an early rider program. So you could sign up for an early ride in fully autonomous vehicle, so without drivers, in the Greater Phoenix area in there. A lot of applications definitely enables machine learning in here, including, we just showed natural, also human-machine interfaces, assistive technologies, self-driving cars, and so forth. Now, there are also various types of sensors, and why we need all these sensors? We need, because we want these to work in a real-world scenario. So for self-driving cars, you're trying to collect all this data, and in order to do that in unconstrained condition, you need a lot of sensors, from cameras to infrared to LiDAR, etc. So some sensors work under certain conditions, other works on others. So you need all these modalities for robustness. On the other end, however, because with mobile devices on the go and portability, and people requiring also more sensors on these devices, we do have a range of sensors from low end to high end. So low end are more and more being pushed. These are very thin, like we saw the Sony thing. So low cost also, low profile, meaning it's small size. But with that come also low resolution, because the smaller the size of the sensor, it's harder to get high resolution. So you get some blur, and also low signal to noise ratio, so you get some noise with that. On the other end, definitely you have the high resolution, but it's more cost, more power to spend, and plus you cannot embed it everywhere. We're talking about data exclusion. So with your cameras, you're taking a lot of images and videos, and according to a Cisco white paper, the mobile video now is 80% of the internet traffic, almost 75% now. In 2019, it's going to be 80% of the video traffic. But more than that, I would like to emphasize that this is a consumer-grade video. What does that mean? It's not very high quality. You're taking the videos and uploading them. So it's consumer-grade under low lighting conditions or everywhere in the room. You're far trying to take pictures. Things are blurred, noisy. You don't have these high-quality images being there. And this is what we're getting flooded with. And by the way, the same thing is for self-driving cars. These cars are driving in the wild under unconstrained conditions, different environment, lighting, weather change. So you're taking all these, so you have all this data being collected under various conditions. So you need robustness to analyze this data. So this machine learning is going to analyze all this data, come up with a decision. They need to be robust to work under varying conditions. The sensors also need to be robust to work, so that's why we need a lot of sensors. So consumer grade is important here. And why do we need also machine learning? Because in the same white paper, it's written it would take an individual 5 million years to watch 1 month of video. 5 million years. So imagine you're looking for a video you want to watch. You can't really, over 1 month even, to just see what was uploaded or going over a month on a video here. It would take you 5 months. So definitely we need automated strategy, data mining strategy, more intelligent ways to get the data, mine the data, and process the data. And even for surveillance application, trying to understand what has been posted on the internet, uploaded, what's fake news, what's not. You need all that. But more importantly, again, this video is mostly consumer grade under different conditions. And this brings us to the various types of sensors here. And you can see their performance in various conditions. They have different performance. So what we could see in here, if we have if under different lighting condition in the visible spectrum, if you have a camera, then it's not going to work well in the dark. But if you go to a radar sensor or an IR sensor, it's going to provide you some imaging in the dark, so you can still see the infrared, but you lose some of the features that are provided by the visible spectrum camera. In addition, as the sensor size is decreasing, so low profile, you get blur and lower resolution. So the quality is affected. Also, you get noise. I'm not showing the noise in here being increased. So that's why it's important to have sensors that work under different environmental conditions, and also to have, even if we have really high sensor, depending on the distance you're taking the photo, the focusing, etc., you might have different qualities. So what about machine learning? Currently, the question we're posing here, can the state-of-the-art deep learning and neural networks now, that people claim they can beat the human performance, can they work reliably in the wild under various conditions with various sensor types, and sizes? But before we address this question, to provide some background relevant to that, I would like to bring to your attention some historical perspectives. So first, all of us, we know this is old technologies from the 60s, 50s, 60s, 70s now. So a lot of the current state-of-the-art deep neural network, they still use some of the elements of that technology. So why is now becoming more successful? The explosion of data, the availability of these large data sets being collected and being provided. But most of these large data sets being provided on the internet, especially for training these networks, are really pristine or high quality, lab quality, let's say, images, like the ImageNet challenge, which has 1.2 million images for training that was available and created these breakthroughs showing these deep learning technology can beat the human recognition performance. This is one thing, and on one hand. On the other hand, we have advances in computing platform. We saw our previous speaker talking about the different advances in computing from CPU to FPGA to ASIC to GPUs. So especially, so we have GPUs, parallel processing, SIMD hardware, enabling the training of such big networks. So and that performance. Part of this deep network or neural networks, when you have a lot of layers, deep convolution neural network, which has convolutions in them, attracted attention because if you take before CNNs, CNN for short for convolution neural network, the networks did not really provide that recognition performance, especially ImageNet. The first winning network is the CNN, okay? And showed that it beat the second even winner by a huge margin. So ImageNet's challenges show you some collection of images. You can't see much there, but you can go to that website to check it. They have 1,000 classes, 1.5 million images, but 1.2 million provided for training, other for validation, and also testing. And if you look, it's organized in a tree structure. So you have different category, plants and animals, etc. Here we're showing under the animal category and so invertebrate, etc. It's a tree. I'm showing the garden centipede, some images here. So you have to recognize that we have a centipede in all of these images, and the networks are able to do that accurately. So this shows you the winners. I started from 2012. The challenge started around 2010. But I'm showing in 2012, a CNN called AlexNet was the winner. The second place had an error of 26%, and this is the top 5 error, not top 1. Meaning the network or the classifier will produce you 5 possibilities. If one of them is correct, they count it correct. So this is top 5. If you go to top 1, we'll see, it's going to be low. Later I'll show top 1 results, I think. So it's kind of low. But top 5 error, you can see, whoa, yeah. So top 5 error, 26, but the CNN, this is a convolutional neural network by the supervision group, AlexNet, so 50.3%, so you could see, I mean, the significant here. These here you could see SIFT, GIST, LBP, these are all hand-designed features. So people pick, I want to use this feature blindly, and with the classifier. The previous winner in 2011 was hand-designed feature with this SVM, support vector machine. But now you could see after that, all the winning entries, all submissions had, most of the submissions, if not all, but all winning at least, had a CNN in it. So GoogleNet in 2014 won. And you see the rate cut by half, 6.6%. So tremendous improvement just by using CNNs. The second even entry was VGG assist CNN also. Now, I mean, this GoogleNet beat the human performance at that level because the human had an error higher. So they got a human and they trained extensively to try to beat the GoogleNet network. And after extensive training, that human expert, a single person, beat at 5.1%. This is the best human performance here. The following year, forget it. ResNet, residual, also has CNN component with some skip connection for residual learning, 3.6% beating the human. But again, it's top 5 in here error. And again, 2016, some combination of this ResNet residual neural network with inception of Google they call inception, 3.1%. So you could see, I mean, the error is incredible, and that's why this deep learning gained a lot of attention. Plus, with also what also similar kind of success natural language plus in the neural network, so dropping in the error, significant drop in the error rate. Now, since we're talking about this, and we're going to look at the AlexNet architecture, to understand not everybody has a background in deep learning in here. So I'd like to provide some background. Plus, we're going to use this AlexNet architecture as a baseline and what we're going to talk about. So what's AlexNet? And this looks really complicated, but I'm going also to simplify. So this is AlexNet, but what we could see here, we have an input image. So what we see here is an input image, 220 pixel by 220 pixel. It's a color image with 3 channels, color channel, RGB, red, green, blue. So, and then what you do is convolution. So this is the filter size. So hopefully all of you are familiar with signal processing concepts, and you have FR filters, and you have impulse responses, the kernel of the filter. So these are the filter coefficients, 11 by 11. You're doing just multiply sum, shift multiply sum. You see, so you have filters. But how many filters do you have? You have 96 filters, although we're showing 48 here, but what they did when they implemented AlexNet, they used 2 GPUs, so they split it into 2 pipelines. So that's why 48 here, 48 up, but it's the sum. You have 96 filters being used in parallel. So each filter, so 96 in parallel processing the same input. And all of them, they have 11 by 11 kernel in here, size. The difference here is we don't design the filter, we learn the filter weights. We learn the impulse response of the filter. We learn it from the data. Okay, so that's how you find these weights. We call them weights, or filter coefficients are called weights, kernels. These are the parameters of the network, are these filter coefficients that we're trying to learn instead of design ourselves to minimize some function based on some ideal function we know. You know, we learn from the data. But all of these is convolutions with a parallel filter, which you can think about as if it's a filter bank. What we have a stride of 4. What stride is downsampling. So you just do the convolution and downsample by 4, or you just jump every 4 pixels instead of every pixel multiply sum. So what you could think here is convolution with the FIR filter of 11 by 11, but a bunch of them in parallel, 96 in that first layer, and you have downsampling by 4 in each direction. Then after this linear layer, linear convolution here, you have what we call a max pooling. This is the non-linearity function. What you do on patches that are, here, I want to go back. On patches that are 3 by 3 or whatever you want here is 3 by 3 in this, you take the max. Okay, and it can be overlapping patches on every pixel, but in this case we have downsampled by 2. So you're jumping every 2 pixels up, taking the max of the region of support around it. Then you follow another convolution layer with parallel filters, then max pool, another convolution layer, max pool. That's what it is, and you keep adding. But now you need to learn the weights of all these filters through the data. At the end, you have what we call fully connected layers. Okay, fully connected layers, what they do, it's just they produce you have a bunch of filters also, 2048, but their kernel is equal to the size of your input. So it's not a convolution anymore, just multiply sum one single number. So every filter produces one number, multiply sum, that's connected. It's connected to the whole input. And we generate basically as many elements you have, 2048. The last fully connected layer, typically, you have how many filters you have? You have elements equal to the number of classes. In ImageNet, you have 1,000 classes. So you have to produce 1,000 numbers. And you convert those to probability. They're trying to estimate probability. That's you're trying to estimate what's the probability class I given X. And this is what this is trying to generate. Definitely, you don't get numbers between 0 and 1, so you normalize them. Usually they use softmax function or other functions to normalize between 0 and 1. You get a probability distribution of the classes. You can take the maximum to get your class. Another view of that usually we use in our paper is this. This is much better. So this architecture can be summarized like that. You see the first convolution layer. What this is saying, this is, okay, so this is the size of the kernel, 11 by 11, the size of your impulse response of coefficients. This is the number of filters of that layer, the parallel filter, the number of filters in your filter bank. And every filter will give you an output. So this will give you how many outputs is going to be produced out of that layer. So we call this output depth also, because every filter is producing an output. You have 96 of them, you're going to get 96 outputs. And then the final number, and here is the stride of the downsampling. So you can see here, it's easy now to see what's happening. That's the first convolution layer. It tells you the kernel, the number of filters. Then max pool. On a 3 by 3 patch, you're taking max pool, downsampling by 2. Then another layer, 5 by 5 convolution, how many filters, it tells you here 256, etc. So you could see max pool, 3 convolution layer, max pool, then fully connected layer. And again, this is the number of filters fully connected, each one producing one number. Okay, that feeds. Now to illustrate this further, this is illustration of the first convolutional layer. Okay? You see the input is an RGB image 224 by 224. RGB meaning it has 3 channels, R and G and B. So that's my input. 224 by 224, it has 3 channels, the input depth here. The first convolution layer uses 96 filters. So we have 96 filters, filter 1, filter 2. These are all 3D. They have 3D impulse response actually. When we say 11 by 11, it's correct, but the depth is equal to the input. And that's the difference between what we know in signal processing as convolution. Here is not really a convolution like signal processing, because what's happening is you take that filter, which is 11 by 11 by 3, so it has 11 by 11 times 3 weight. It's a tensor. It's a 3D matrix tensor. And what you're going to do is do a convolution, but you can only slide along the horizontal and vertical direction, the width and height. You don't slide along the depth. In signal processing convolution, you slide everywhere, even in this depth direction. Here you're just sliding here, and you're summing everything, multiply sum. So you're kind of accumulating all these channels, and at the end of the day, you get a just 2D output, width and height. You don't get the depth. So each filter will give you a 2D, one of these. You see? The second filter will give you the next one. Then you have 96 of these generated. See? And what you're seeing here, 11 by 11, and the depth is known because it's the depth of the input, RGB 3. Now you get 96, every filter will produce an output, that's the depth of your output. So every one of those is an output of this filter, and you see basically how do you determine the size? You have a downsampling by 4, so you take the size of your input, you downsample by 4, and you take the size of your filter into consideration, so the edges do not count, you get 55. You see, so you get the output being 55 by 55 in here. And you have the depth being 96 here. And this would be the input to the next layer, the max pool. So you take 3 by 3 patch, you take the max, etc., downsample by 2, and the input of one layer is the output of one layer is the input of the other. So that's how, in short, briefly, how this CNN would work. Okay. And at the end, the softmax function, when you produce this 1,000 output, if you have 100 classes, it will be 100. But you normalize to probabilities using the softmax to get the probability of a class, probability I, class I occurring, or probability J. So now the question, going back to our question finally, can DNNs are robust enough to work in unconstrained environments? And this is an example to show you. We're the first one who showed that actually they are not robust to work with different environments under different quality. Especially now we have different sensors, low resolution, high resolution, etc. And this is an example. This is from this is a bird, a grambling from the ImageNet data set, I believe this one, yeah. This is the high quality original image. Now, as we kind of simulate here different sensor sizes, the size is decreasing, so lower resolution. You could see that bird became a can opener. Even though as human, we could see still a bird, no? Then became a safety pin and call, etc. The same happens also with noise, but here I'm getting another image with a higher confidence. The network gives you some confidence when it classifies something. So that had a higher confidence. At noise level 1, because it has higher confidence, it's still a goldfish. But then as you increase a little the level of noise mode, it became a starfish, etc. So we have a problem here. So before we showed you that these DNNs are beating humans when you have these pristine high-quality images. What about now? We could see that we could recognize the fish, the bird. So can humans beat the DNN? Or can human also, if maybe this is one image, what if we do it on the ImageNet, or on like more classes, what happens? So we did 2 experiments. In experiment 1, actually we used the cloud-based Amazon Mechanical Turk, where we had subjects, we developed interfaces actually for them to take over the cloud, the test, and recognize images with different distortions. And at the same time, we used the same training, or the same images, training and testing that provided the humans to the DNN and compare the performance. In experiment 2, it was more controlled lab in the lab. Why? Because in the first experiment, we didn't have any time constraint. It's free viewing. They could take all the time they want. But we made the categories more difficult. We'll talk about that. In the second one, we wanted to know, can the early human visual system still be the DNA, not higher? Because if you give all the viewing time, you could use the eye movement, higher level processes, kick in. And maybe you can beat the DNA and that. What if we just forget about higher level processes, the visual, early visual cortex, or early visual part of the visual cortex? So in that case, part of the literature, in the psychophysics literature, they use 100 milliseconds. You flash, can you recognize? And we'll see kind of the result. So experiment 1, we had 15 subjects from the Amazon mechanical tour. So free viewing, you can't control anything. They had displayed and whatever. We took the 10 dog glasses from the ImageNet. Why dog? Because it's hard to know what dog it is. It's more difficult. You have dogs and you need to know exactly what type of dog it is. We had, however, more time. And each class in ImageNet has 50 images for validation purposes. So we split those into training, half to train, like we do for the DNN, 50% for training, we wanted to use, and 50% for testing. Out of this testing, 5 were used for validation, clean images here to validate that the subjects are classifying well and to remove outliers, if any. 20 images, we took them and we produced simulated blur and noise on those 5 levels. So this gave us around 1,200 images for testing. So after we added these levels of blurs and noise, etc. And these are examples of the stimuli for the dogs. You see, these are the original dog classes, and once these are the level of blur, you could see at a high level of blur, you could hardly see anything now. In here, it's tough, but you still see kind of, so but it's becoming really blurred here. And noise also similarly, this is with noise. Now, how did we do? First, I'll talk about that as well. So we had a training interface where we had this, for people to familiarize themselves with the training categories of the dog, what dog categories, they have to look at clean images of the dog. It's like the DNA, just go through it, and they had to go through it. We designed our interface, they cannot continue until they go. So they start, they have to go through all this until they finish and look at the dog categories. After that, we had a validation stage where we did testing, but without them knowing these are validation clean images, to know whether to measure some things about their performance. And then the testing stage in here, we don't want, with 1,200 stimuli, we don't want, this is too long. So what we did is, we start with the highest distortion. If you can recognize the dog at the highest distortion in that category, we assume also the same image at lower distortion, you should be able to recognize. So we start with higher distortion first, and randomly we display images at the highest distortion. But once you recognize an image at a high distortion, we don't show you the lower distortion one. And we do the same thing for the DNN also. This is our testing interface. So you can see this is through the cloud. We did that. So you have a noisy image here. You have to give us what it is. These are the 10 classes. You have to click on one. Meanwhile, however, you could go and see your training data. If you forgot kind of the category, what's a German Shepherd, whatever, you could do that. And once you decide what it is, you can click and say continue. So once you decide after review, you say, oh, it's a border called here, and continue, and then you get the next image. That's the testing interface. And we found out of 15 subjects, only one outlier that had really on the validation region, very low kind of or high error rate on the validation test, not doing their job. But it's impressive that these people on the cloud, they're from everywhere, and they were very consistent. On the validation set, they kind of 93%, and the standard deviation was kind of low. And they took 6 seconds per image, and for the training time to go through, it's 11 minutes. They are consistent and diligent. I recommend Amazon. This Amazon mechanical check, they're pretty good. I was impressed. Now, to compare with the human, and I'll show you the results, we chose state-of-the-art DNNs, including GoogleNet, ResNet 50, that's and VGG 16, to compare with that. And each network was trained using the same, first the weights, the initial weight were the ImageNet weights. So they are pre-trained with ImageNet, which gives them, we're not going to get from scratch. So this gives advantage to the network. They are pre-trained with ImageNet already. In addition, however, to recognize only 10 classes instead of 1,000 class. Remember, we had the 1,000 fully connected, we now 10. We only replaced that 1,000 with the 10 and trained it with our images just to recognize these 10 classes. We learned that later. And we did the same procedure also. We start with the highest level of distortion. If it's recognized, we assume the DNN, we give it a bonus that it recognizes everything. So actually, we're being nice to the DNN here. The DNN can be lower even performance. So these are the results. This is on blur. So resolution, how the sensor side resolution affects the prediction. The top curve is the human, and this is the blur here. The higher the sigma, Gaussian blur here to simulate the sensors, resolution and sizes. This is the highest blur. You could see the human curve is pretty it decreases smoothly. This is the DNN. At zero blur, yes, they are on par with the human performance. You see the DNN performance at zero, high quality. As you add blur, boom, exponential decrease in all the state of the art. But this is again when the DNR are trained using these ImageNet high quality pristine. What about noise? Is this better? Noise is worse. Actually, human, they do pretty good in noise. You see, it's like high, it stays high pretty well. The DNN, however, is the reverse. This tells you the pre-DNN, they're not modeling exactly our human vision. I mean, still there is a way to go, especially when things are distorted and a little bit off what they train on. Now the question is, what if we add part of the training set these distorted images? Not for the human, we're not going to add it for the human, just for the network. Okay, we add that. If we do this, and we train now, we include these, this is what happens. Indeed, so the dashed are what we had before. The solid now is after we add in the training the distorted images. You could see basically things went up. Still there is a gap with the human performance being on the top. Still they didn't beat the human performance. And things, however, improved the performance. Still, for example, the ResNet one, the best was VGG actually, which is lower than the ResNet supposedly on pristine images. Now for noise, however, for blur it's not bad. For noise, however, even the fine-tuning did not have much. You see the gap is really big. And worse than that, you could see here that ResNet is doing the best here. And before, VGG was doing the best. So, which one should you use under different conditions, blur and other? You want like a consistent platform. That's also the problem. You don't want to switch networks. To just illustrate more, this is the confusion matrix. This is human, these are the classes. This is class 1 to 10, 1 to 10. This gives you the number of images that got predicted correctly from that class. So, for example, in class 1, if you have a diagonal, this means perfect prediction, almost. So the darker mean 100%. So this is the same class. So in class 1 here, this is class 1. How many images from class 1 were in class 2, 3, 4? So if you see colors appearing, this means some images from class 1 got. So if you see any leak from the diagonal, this means worse performance. It should be diagonal. And you can see the human is pretty diagonal. When we go to the DNNs, and this is without adding the distorted images, you can see things. They tend to just group things in two classes, which is totally wrong. Now when we add distorted images, it becomes better, but still at high distortion is also not good, and the human is still the best. For blur and noise, we get the same thing. You see, this blur, that's noise. Now, what about the second experiment with 100 milliseconds? So just flashing these images, 100 milliseconds. The DNN, they don't need to flash. They have all the time to compute. For the human, we're flashing. We had, however, easier categories because you don't want to have dog flashing. Forget it. So we picked classes from the ImageNet here that are, so that are separated more in the categories. Like you could see elephant, whatever. Can you tell that? So these are the blurry stimulus, noisy stimulus, and we did the same as before, except the testing interface is different because of the 100 millisecond. I want to show you the testing framework. Because it's 100 millisecond, we want them to fixate in the center where they're going to be. So we have the cross here, they fixate. Then 100 millisecond, the stimulus fixate again. Then you have to choose one class out of 8 classes, elephant or so some fish or whatever. Given that now these are the results, and here we have the fine-tuning in addition. So the human is on the top. These are the DNNs here, the VGG and ResNet and GoogleNet. These are my DNN without being trained on the distorted, just the high-quality images. If I add distorted for blur, they're doing pretty well. This is again the human, we're given 100 milliseconds in here. But this is again here, the accuracy that we're looking at is the top 5 accuracy here for the DNN. This is with noise. Again, the noise performance is on the high quality is similar to before. When we fine tune is up. However, you have the same trend. The different network on noise perform better than on blur, and you don't have a consistent frame. So human can recognize distorted images even when the display time is very fast. So this is using a very low level of the human visual system, just level information. We call it TNN perform always worse. And especially if they trained on high quality images, or even if we have trained on distorted, it's not consistent the performance, and with the high level of distortion still there is a big gap. So what can we do? You could restore your data, say, oh, I want to do denoising, I want to do blurring always, and then feed it to your network. But also this is computation intensive, and we don't know what to deblur and etc. and denoise. Instead of that, instead of restoring the data, our main idea here is to restore the features in the DNN. What's happening? That DNN was perfect, recognize the image. We add some distortion, a little bit of blur, nothing. Something got corrupted there. What's getting corrupted? The features, the filter outputs. We call them features, the filter outputs that were generated at every stage. They're called features, or they're called activation. So these features, filter output being generated at every convolution layer, they're getting corrupted. Can we fix those instead? Can we find the features that are corrupted? So one question is the corruption everywhere? Are all features corrupted, which is a problem then, we have to restore everything? Or is the corruption just concentrated on some features, in which case, if we could mask these features and regenerate them, transform them, correct them, we should be good to go. So that's kind of the idea. Can we transform low quality features into high quality features? And if I can transform low quality features to high quality coming from low resolution data into features that look like the high resolution data, what's preventing me from taking any sensor modality, radar even, converting it to RGB features? So that's kind of the power of that. You could take any features from any modality now, learn transformations to transform these features into other modality. And this is what we call generative sensing kind of framework. We started this work, what we call is deep correct. We're trying to correct these features. So we found that actually just a fraction of the features get corrupted. And we can learn transformations to corrupt them just by correcting these features. We can add some small blocks, even CNN blocks, or whatever. You can learn model to transformations to correct these features, and you can achieve a lot of performance. But as a generalization of that, we're proposing this generative sensing framework now, where you could transform any feature to another one so that you can achieve higher classification accuracy. So goal is transform a low-end, low-quality sensor into a high-end, high-quality sensor. And sensor here is associated with data again. Sensing, so low quality, meaning low quality data getting out because of the size of the sensor. It's high quality data. But here what we're interested in is high recognition performance and high classification performance. Now, there is existing method now trying to doing image generation. Like DNNs are being used to generate new images or style transfer. You draw some pictures, you give it to the DNN, you train it on your style. Now you just take a photo, it will transform it into your style. So that's as closest to kind of what we're talking about. But what they do is they care about generating an image at the end and care about similarity to a reference image. They don't care about classification performance. I want to generate an image that looks nice. So existing work include colorization, how to take a grayscale image and make it color, and then you have a reference and you can have a similarity measure, or basically artistic style transfer that we talk, or data set augmentation. A lot of time you need to train the DNN, you need data. but you don't have enough IR data, for example. You don't have enough thermal imaging data. So what they do, they try to generate fake IR, so synthesize a model to generate an IR image that they can use to train the network, infrared image or thermal generation image. But again, they don't care about classification performance in this image generation. In our case, that we want to generate features here, not the image. The features so that to improve the classification performance. And so we use basically target function for that classification, for discriminative model for classification, like cross entropy and whatever. So this is our framework here for generative sensing framework. You have a neural network that have been pre-trained on high quality sensor data. So this is already trained on the high quality. Now you input a low quality sensor data or low end sensor. It goes through that same network that have been trained on the high quality. You have feature maps. These are the filter outputs. That's what are feature maps. The filter output from layer 1, the filter outputs from the convolution layer 2, etc. All these feature maps. Now you compare these feature maps here. This is the high quality feature map. It went through the network. Because this is distorted, it's going to be distorting these features. Here it's like whoever working here on image quality or whatever, quality assessment. Here you want to see quality assessment of the feature, and you have a reference. This is through training, by the way. It's training stage for our generative sensing framework. So you find what is the difference in feature, but not in terms of difference, in terms of classification accuracy. And to give you a little bit some intuitive way, for example, to do it, if you take features from here, collocated features, if you replace the low quality feature, what I'm going to call, with the high quality, how much classification improvement you get? Just by replacing it. This is the perfect correction. Then you can rank these features and see which one affect your classification. And only learn transformation for those. And we found few of them we can learn for few, like relatively, not all the network. So this is my delta phi. That delta phi can be a drop in classification accuracy for the different features. It tells you a drop. From that, you could decide to select the feature to regenerate. Now, after you do that, you regenerate the feature, you have a network corrected already that you could use here. It's just, in testing, you just use that network. So again, so find collocated features that are significantly different based on classification accuracy. That's the delta phi. Values of difference maps can be classification accuracy drop for each feature. You can threshold it to find the mask if you want. Regenerate feature whose delta phi has a significant drop. So, and how do we regenerate feature? We perform it purely by learning transformation, learning them, because you don't have the ground truth. You see, you can have training data, that's what you could use. So you need to learn the transformation to apply it on any later in the real world. So we learn these transformations. And how do we learn, basically? We're going to see. So in our case, we learn by using small convolutional or residual learning blocks that have much lower number of parameters that are applied only to the output of these filters that we found that are susceptible to noise. Only to those we apply them. So the generative sensing network would be the original network, but just we add these transformations on selective filters. Let me show you. You know the AlexNet. That's our original AlexNet. All we do after we rank the feature, and this can be improved on how to rank feature, how to find the features, etc. This is all you can do automated. So a lot of research will be open because of that. So once you find your susceptible features, suppose you found them. In this case, we split. So the feature out of the 96, suppose I'm showing here, we're correcting 72 of the filters in the first layer, and 24 are left uncorrected. You apply a generative unit, what I call, or transformation. This generative unit is just to regenerate, transformation. What is that? This is this network. It's a small network, convolutional based. It's a residual network. You see the skip connection? This is the form of a residual network. All it does, if you look at the output is just the input. Suppose the input is x and the output is y. Y is equal x plus this. So this is a residual. You're learning the residual since y is x plus that. And they are powerful because you could learn now with fewer parameters. You could it gets you some memory in here, and and you can learn with fewer parameters better. So with this small network, and you can control the parameters, the K here. We add these generative units in here, and definitely, the first layer we found to be the most important, and you can correct in other layers, and we're going to show results. But that's the idea: correct selective features in your network. Now, these transformations can be used to transform features from one mode, like infrared to RGB, for example, and so forth. So the transformation can be estimated by determining the weight of this residual network now, such that when we apply it, we have this 5-gen net now applied to the input, and this is a classification loss function. Yi is the class label you want to estimate, or you want to estimate y given x. So 5-gen would give you, and this is a loss function in here. And usually it's a cross entropy function trying to estimate the probability y given x. And you're trying to estimate that. So in addition, you have some regularization here based on some prior. This is the prior of the weights. And W are the weights of that network, the small network I'm showing you. But we have some, M here is the number of also total number of data samples in the training set, because you want to overall that training set. So you can have different loss functions. This is one of them. This loss function is flexible how you design it also, depending on the application, and this regularization function also is flexible depending on your prior that you estimate. You could use N1, N2, etc., and others. So we can optimize that function to find the optimal weights in here. So just to show you the feature maps, so these are feature maps from conv layer 1 of the AlexNet. We selected some outputs of the filters. Remember, we have 96. We selected some of them for illustration here. This is a good quality image, and you can see the feature map. This is with blurry, low quality, low resolution. You see the feature map being changed, Now with our generative sensing framework, and this is not optimized, by the way. These are initial results. You could see that we're retrieving, we're not retraining the network. We're just applying these units and just learning these transformation on the feature. We're not retraining the whole network at all. So we started with the high quality network. We just add these transformation units on it. So it's part of our network now. And you could see some features getting restored, getting closer to that high quality image. Okay? These are some of the results. Showing this is the baseline, is the AlexNet. But we have also, to be fair, what if we train the network with the distorted images? We don't want to compare to the baseline. And this is what's showing you, fine-tune, meaning I'm retraining the whole network. And AlexNet has 61 million parameters almost. So here I'm recomputing the 61 million parameters. Whereas with our generative units, all of them, we have 2 million only, or 3 million, let's say, versus 60 million. Just by computing, retraining the 3 million, we achieve better than fine-tuning. All these bold are the best. And this is top 1 accuracy, by the way. You see the top 1 accuracy is here, 0.56, 56%, 57 on ImageNet. This is top 1 accuracy. Fine-tuning, so we kind of achieve. And you can see even at a blur that's very high, 0.43, we're like the low blur. You see, the very low-end sensors, suppose, with very high blur, can achieve classification accuracy as a high-end sensor with a little bit of blur. See that? Is actually similar. Whereas the performance drops very badly if you don't do that. And the fine-tuning is stable, but also is very, still is not that great. And you have to train all the parameters. Now with our generative unit, you could also do incremental learning because you have to train only these generative units. So if you sense the environments change, lighting conditions change, you could also relearn the transformation in an incremental learning, which is more dynamic rather than training the whole network offline. It allows you that also. Now, however, we said, okay, we already trained our network on the ImageNet and also on RGB images, distorted, etc. images. We learned the transformation. Ideally, we want to get IR images and also do IR to RGB or whatever. But we want to see how generalizable they are. Can I take that network as it is and apply it to different applications? ImageNet is object recognition. Can we apply it to face recognition now? Using the same transformation we learned, we didn't change anything. We're trying to apply it to another new data set, the ST face data set for face recognition. They have IR and they have RGB. And what we're doing, we here also added blur level to simulate low resolution sensors and different sizes on the IR, on the RGB. And just applying our network to these, we only changed the last layer because for the classes, here we have different classes, 130 subjects. So the last layer instead of 1,000 is 130 now. Look, the baseline RGB network, so this is just taking AlexNet and applying it to the face images for face recognition. It does good at high quality. So you see, I mean, these neural networks are powerful when you do transfer to other sets, so it does good. But as you add blur, look, it becomes really bad. With our generative sensing, just adding these few units to select features, you keep the performance pretty high. At 2 blur already is 43%. We're already 90% still with the generative sensing. You see, you push the level up. On the IR is the same. The IR, even though we applied RGB kind of learn transformation, we also achieved the same robustness and much better than the original network. And I'm going to show you now some features, how they look. So this is the RGB features. So this is the good quality features, the NN feature map, which are the output of filters from Comp1 here. Lower quality, you see the features like reduced, here. When we go to our generative sensing, we're recovering the features. Now the interesting thing, when you look at IR, the features also get reduced, but when we recover them, also because we use these transformation trained on RGB, you could see closer some of them to the RGB in here. We apply it for scene recognition instead of object recognition and face recognition. This is from EPFL, the RGB and IRC data set, and they have near infrared here. We wanted different modalities, hard to find match different modality, by the way. We need your data, radar with RGB or whatever for classification. So that's needed. So that's the original and different blur value. This is the NIR. Also we applied our generative sensing framework on that. You could see also similar trends that while the baseline AlexNet decreases in performance significantly, we keep the performance very stable with our generative sensing for both NIR and RGB in here. So what's next? Concluding remark here. So despite the fact that we don't have data to train even IR to RGB, just reapplying our generative sensing framework, which we learned on using RGB images, ImageNet, and distorted, worked well and generalized well across other data sets and other applications with significant improvement compared to the baseline network, the AlexNet network. And this applies, by the way, with other networks, BGG, GoogleNet, if you apply these. For example, for the SC face dataset, our generative sensing features significantly outperform the baseline with 103% and 105%. 103 for RGB percent, 105 for IR. Same thing for the PFL dataset, 40 for RGB improvement over the baseline and 50% in IR. And this also the large gap in performance between our framework and the baseline that were much better shows that the generalization of our framework to other different applications and modalities. So now you can have one single network that you can apply in under different lighting conditions, different modalities. You don't need all these different data and switch networks, etc. So future direction, we need data sets. We need data sets having matched the same scene, RGB, IR, radar, etc., which is being collected by cars now. So we can make use of some of these sets. Also, demonstration of generative sensing with actual training with various sensing modalities. Also, investigate other learning models. Now we use this ResNet to learn this transformation. You could use other learning models to learn these transformations. Also, development of generative sensing, low power, low cost sensing platform, 201. Develop that and integrate it and demonstrate this. So these are some of the future directions, and you could think of more also. I can take some questions now. Thank you. Yes.
So since every image is a visual image, a combination of
since every image is a combination of high frequency component and low frequency component, like age information and objectness, like the blurry image objectionary. So since like all the CNNs are very good at capturing the high frequency component, the age information, because of initial, if you see the initial, all those activation maps, they are like Gabor filters kind of thing, all those ages detectors. Yeah. So your network, this generative sensing, is somehow capturing the low frequency component, I'm saying?
You know, when you get blur, also you're getting, we saw that in the feature map, the edges are getting corrupted also, because the blur is capturing edges. When you have noise also, the noise is masking these edges also. So also is like this, is also whatever information needed for classification. So the DNS, with the high quality, they're getting this edge information. It's still, it's regenerating this, I would say. Definitely with the gist, if we use gist level as human, we use actually the texture, the image, the gist, even not only the edges. And this is something to incorporate also. And we hope the networks are learning that, they're not doing it well. So how can you develop network to learn better the low frequency or gist information? That helps also the recognition better. That would be good to do. Yeah.
Just curious to understand, what is the infrastructure cost that it takes to, compute infrastructure cost that it takes to get all your training set, learning, training, all the stuff? How much?
So infrastructure, to tell you that all you need is like GPU, machine with a GPU. For example, is this what the thing? I mean, you need like...
I was just seeing an example of the recent Qualcomm 850 processor.
Okay.
They published this processor. So they do this image processing. They put it in this ATMs and they try to do some image processing and see who's...
So you want like on-the-go image processing?
The problem is, for the training part,
yes.
For whatever training part, they keep capturing images. They have to push it out to the cloud. And since even with a massive processor, you still have to offload much of the training process into a cloud. It's a massive infrastructure, I assume, would be the case.
So you want to do it on, like, you're not... So the question is it like, because we work on incremental learning, where we want to do incremental training, a lot of time things change and you want to do it incrementally, so you have incremental learning framework that can help do it incrementally, and you don't have to train. So definitely you have to pre-train your network, and then you can incrementally update the weights. You train it offline usually.
I agree, but for the offline training you need a big cloud infrastructure.
You don't need a cloud, you can do the Amazon web, definitely. Amazon cloud or Azure, definitely. But all we need, I mean, we're using machines, computers, with, Linux machines with NVIDIA GPUs or NVIDIA GPU, Titan X GPUs. And you can train on those. Even I had my student before we got the GPU train on CPU, but it took like a month instead of a week or a few days. So with the GPU now, I mean, you can train easily. I mean, you don't need cloud. If you don't have GPU, I'm teaching a deep learning class this semester. And for the student, we're working with the Amazon also web for them, for the computer resources. But a lot of the first few labs, they can do it on the CPU even. So to do some prototypes to test your idea, you don't really even need even a GPU, because you could take a smaller training set and train on that and show the prototype. Once you're ready to go, now you could really train on a bigger one, and you need a GPU, or you could use the cloud. So you don't need to use cloud platforms.
The question I was trying to get at is, all this, when do you think this will really realistically hit any product?
Yeah, I mean, for testing, by the way, they are fast. Only the training is what's required, and training you can do offline. Testing, it's just multiply sum, thing. So it's really testing, it's like we found that TNN is faster even than other computer vision algorithms. You could do really real time. No problem with the deployment of products.
Now, there's incremental learning, which itself could lead to noise or distortion, which,
Once we train our transforms, that's it, it's fixed. Then you could just use the network. So on one slide I showed the testing just using that network, multiply sum. You need to do, it's like to train your network, you need to do it once the training. Now you could do incremental learning, adaptive if you like.
The incremental learning can also be unlearning, right? So I'm just trying to be critical here.
Yeah.
For example, you apply this into a live taxi in a connected car.
Yeah.
You're going. So there are random images which are coming in. That's part of your incremental learning.
If we
Those
consider
also, I mean, we saw the figures,
Here,
blur
here is
and
train
noise.
offline. I just want to clarify something. Here is train offline. Here you collect data set like the ImageNet, whatever. You have distortion and things, but it can work in the wild better. That's what I'm showing. We simulate the senses. It's offline training. We're not saying online. We didn't go to the online yet. This is just you train like you train your network offline. Then you deploy like the current network. So it works really. It's ready for product, basically, I would say. I mean, it's just like as ready as the deep learning now, CNNs for product, this is ready. No problem. Now, if you want to do incremental learning, that's a different thing, even for the current DNNs. And we're working on strategy for that. But our technique doesn't require it. It's all offline training.
So there is somebody in the back.
Maybe can we have her question while the microphone? Yes, please. Go ahead.
So ma'am, you said your baseline was the training on the good quality images. Just by intuition, did you ever try to use both the good and the blurry images
The
together?
fine-tuning I've showed is using both. So when I say fine-tune, we showed that, and we showed we're better actually than the fine-tune. So the fine-tune is again training on distorted images, but we don't want to start from scratch. We start with the initial weight from the ImageNet, and we add the distorted images on that. So yeah, definitely, that's a good question, and we did it.
Thank you.
Yeah, sure.
Initially, you have trained the neural net with distorted images, right? For improving the accuracy of the output.
Excuse me, what was the question?
No. Actually, my question was, initially the accuracy was very low when you showed for the classification.
Yes.
Then you trained the neural net with distorted images for improving the accuracy.
Yes.
Yeah, but what is the need for training the neural net with distorted images? Instead, why can't we use the deep learning and filtering the noise out and then enhance the image and then give it for classification?
So that's another approach. We said when you want to do data restoration, it's not in it. So the problem with that is if you apply restoration blindly, you might corrupt your data. So you have to have now incorporate image quality assessment first to assess your data. Is it noisy and what technique to use to do it? You know, and restoration is complicated, so you need another not only network. You could do, restoration without deep learning even. We have some, or you could use deep learning to restore. But this is doing it end to end. You don't need to have a restoration then followed by classification. This shows, we're integrating it part of the learning. So exactly, you're learning inside how to restore the features. A lot of time when you want to restore your data, you might not restore it for the classification. You might restore features that are not important for your classification. So why waste resources and power on restoring something that's not needed for your recognition? So here we're showing you no, just focus on your recognition, and we are restoring the data. We are restoring only those features that are important for your classification. It saves on the parameters, on the computation, on the power, instead of regenerating everything, and you don't need it.
Yeah, but can't we make our neural net to restore the image features that we want?
But that's what we're doing. That's the whole idea here.
Here we are training the neural net with our distorted image, right? But can't we make our neural net to deep learn and filter out the noise?
No, we are learning with the distorted. We start with an undistorted network. We add, so yeah, we are learning with the distorted images, but instead of retraining the whole network, we're only correcting the important feature and learning only those. That's the difference. So the training is with the distorted, but we learn only these parameters, these generative transformations. So we only learn the features that need to be learned. That's the only difference.
Yeah. Even though the computational power might be required, might be a lot of high, but what I mean to say is, even though computational power is high, but the accuracy will be high, right?
No, I showed you the accuracy is lower.
No, here you are learning with distorted image, but if we try to do image processing and try to enhance the image by deep learning and removing the noise, won't the accuracy be high?
No, because it depends on your application and whether you did it right. You might, again, you cannot distort the image what you're doing, and it requires compute resources and etc. and denoising. Everything requires more resources. And plus, how do you know what to apply, what noise it is? So you have to have image quality assessment in addition to the right algorithm to denoise it. And we know computer vision, they don't work well on different platforms. You have one thing for it specific. So it's better to do a learning platform that immediately adapts to different things. Yeah, that's my opinion.
Yeah.
But
Yeah. I have a question. Yeah. Yeah.
okay, yeah. Oh, I see. I'm looking because there and here. Okay, oh, sorry. Yeah, I see you now.
Yeah.
Sorry.
So, how do you determine boundary between while training a data set, whether it is overtrained or it's absolutely perfectly training? Because if the data sets get overtrained, it doesn't classify the data
That's very
sets.
good. We use the validation
How do you
set.
determine that boundary?
Yeah.
So how
Yeah,
much?
so what we do, we have a validation set. I didn't talk about, but typically when you train, always, you have a validation set that you test your training on to see if you have any overfitting or anything. And based on that, you decide to continue with the training or not, until the error decreases. But there are ways to kind of test for overfitting. And typically, so we can train to kind of avoid overfitting, I think.
Yeah,
So
but
we can take
it's-
it offline if you want, and we can talk about it.
Yeah.
If you want, we can talk about it offline. But there are different ways to test for overfitting and not overfit, even in the learning. So we didn't go here inside the learning thing and how we do it. And this is common, why I didn't discuss it, because it's common for deep learning now. People are doing that to avoid overfitting, so it's not something we created. I don't want to focus on that aspect. Yeah?
One more question. So if, while training the data sets, it may work well, but while during in offline, but when in real time, so it may there may be some outliers present in while they're working in real time. So how do you differentiate? So
Yes,
it-
the
so-
generalization.
Yeah,
That's the
so-
whole thing. I mean, we have ways to test for generalization error and estimate it. So that exactly what you're saying, it works in the real world, because that's why we're trying to estimate all these DNNs and CNNs. They're trying to estimate the data generating process, what the probability, because everything is random. That's why we assume things are random, and we try to assume the probability.
yeah, I can understand. So
and
you
if you estimated right, you should be able to apply it to other things because you estimated the probability, the data generating process. That's the whole thing, and there are methods to test for generalization and everything for that. There are different methods to do that. And it's like independent of whatever work. I mean, there are methods to do this.
So in the interest of time,
Maybe you can take it offline and
Thank
discuss
you.
it outside. That's
Yeah. In a slide you showed that that machine is learning as a can, then a hairpin and something else, right? So human sees it. The first image is very clear. The second image is human is already biased of it being a bird.
Very good point, very good point. That's why we randomize. We don't show the next image immediately. I mean, we randomize. We do, not based on memory. It's all randomized. So I'm not showing the next dog in the same. Everything is random when we present it to the human.
Okay.
But if they recognize the high distortion, we don't show the other images that are lower distortion. But definitely when you do these subjective tests, you have to take that memory into account. And if we wrote a paper about it, like it was presented at ICCB, we talk exactly about this, the memory effect and how to avoid them. And we said we designed our subjective test to avoid this memory effect, to make sure this doesn't happen. It's a very good point.
So I have a question for you. So this is a rather kind of a simple thing. So when we do pooling, why do we always do max pooling? Why? I mean, there are many other ways pooling could theoretically be done. But how is it that max pooling works well?
Yeah, so that's a very good question. I didn't go into like the theory of that, but from machine learning literature and everything, the pooling strategy. So the max pool versus the average pool, for example. I mean, at least experimentally has been shown to work pretty well and to beat average pool and everything. I didn't go into the theoretical justification for that yet, but that's a really good valid point to look at the max pool. One thing, however, with max pool that I know based on our work is it's trying to, it's like, it depends on your application. What's the most influential there? Averaging, you're taking also things that are weaker. But in classification, what's the thing that's more influential there? That's really doing the max. And it depends, again, how you set up your system. But in this system where you're trying to compute features and you want something that stands out, the max gives you that. But there are some, studies on this. I didn't really delve a lot into details into them, but whereas averaging is going to dilute your features and take something that's not important. The max score is taking the important part.
Extremes rather than averaging out things.
Yeah, averaging out things. Here you want to just extract the important, and averaging want to dilute this important, whereas the max is making them more pulling them out. But there are some studies on the pooling strategies. I cannot comment on at this stage.
Is there any more questions? So if not, then let us. So one more. So that would be the last question.
So first of all, I'm not very familiar with machine learning, but I have one question. You have shown the architecture of AlexNet.
Yes.
So you choose a kernel of 11 by 11 using the 96 level and some layers. So
and all layers, they have different levels.
So how you come up with that architecture? Is there some mathematical background that this architecture will work? So
very good question. I mean, a lot of time, that's the thing. It's like arts and science. They tell you medicine is art and science. Sometimes engineering can be arts and science, especially in deep learning. That's just usually, I mean, people have different so that's a very good question. But for example, let me give you VGGNet. VGGNet is all 3 by 3, you see? And it's all uniform, and what can you do with that? I don't know how AlexNet, they came up with 11 by 11 followed. I don't know the literature. But the important thing when you design this architecture, if I was designing, I want to minimize the number of parameters while achieving the same performance or better. And that's why, I mean, VGG, I guess they take 3 by 3, although kind of it was longer in depth, so it ended up having more parameters. But now the GoogleNet, they came up with an architecture with much lower, instead of like 160 million for AlexNet and 140 million for VGG, 7 million only, 4 to 7 million, some version 7, some version 4. By being creative and using smaller kernel, different sizes convolution, instead of one, they use like 1 by 1, with 3 by 3, with 5 by 5, put in a more scalable structure, tree structure, to different levels, to come up with this inception module to minimize the number of parameters while achieving good performance. Maybe going through that paper and reading it would help you see how the architecture is designed to have their aim. A lot of time, however, people are just trying, but I prefer to have something more justified, and you have a purpose, and I'm trying to do that and set it up. And I think you can find some of that in that inception, GoogleNet inception paper, how they design it to see. But other than that, people just add layers, try to learn these parameters. Sometimes it can be ad hoc. I'm not really for the ad hoc. I prefer to be working. That's why finding an issue and working on solving them. We started with a baseline. Can be any baseline that we can apply to, here, and focusing on that aspect. Yeah, that's my answer to you.
So let us close the question and answer with this, and I'll present a token of appreciation from the IIT to Professor Karam now. So with this round of applause, let us close this session and head over to lunch.